So in class, we learned about the law of cosines, and basically it gives us a relationship between three sides and one angle of any triangle so that you can find the missing information. And in class, we just were given the formula, but in this video, you have the chance to see the proof of the formula, so where it came from. And all of the mathematical steps in this proof should be familiar to you, except for one. So I'm going to give you one extra bit of background information to start with. Okay, so if you were to take any angle, let's say 42 degrees, and in your calculator, if you were to find the sine of 42 degrees and square it, plus the cosine of 42 degrees and square it, you would get 1. Any other angle you choose, like 263 degrees, same thing. The sine of 263 degrees squared and the cosine of 263 degrees squared is also 1. And you could grab your calculator. You could pick any other angle you want. It could even be negative. Whatever you like, your favorite number. Maybe it's 102. Whatever it is, if you find the sine and then square it, and the cosine and then square it, and then add those together, you always get 1. So that's known as a trigonometric identity because you always get the same thing no matter what you plug in. And we can generalize it and say that the sine of angle theta squared plus the cosine of angle theta squared is always 1. Now actually the way we write this is a little bit different because instead of writing the sine of theta with parentheses around it and then a squared symbol, we just simplify it and we write sine squared theta, means the same thing, and then we write cosine squared theta. So sine squared theta plus cosine squared theta equals 1 is a really important relationship that's going to come up in the proof you're about to see. Now remember, the reason for the law of cosines is because we have the law of sines, but the law of sines won't work for all triangles because it just depends on what pieces of information we know about the triangle. So if you know certain amounts or certain info about the sides and certain info about the angles, maybe you can use the law of sines, but maybe not. And the law of cosines gives us another option. And we want it to work for all three types of triangles, acute, right, and obtuse. So I'm going to go through a three-part proof showing that it works for all three. So I'm going to start with an acute triangle. So I've drawn acute triangle ABC. I've dropped a perpendicular from angle B and labeled that length Y. And I've labeled the sides A, B, and C as well. And then the perpendicular causes us to have two small right triangles, and so I've labeled the length here X. Okay. Now, using the right triangle on the left, we know that the cosine of angle C is adjacent over hypotenuse, and that would be X over A. And using the same triangle, the sine of angle C would be y over a, opposite over hypotenuse. Now, if I isolate x in the first equation, I get x equals a cosine C. And if I isolate y in the second equation, I get y equals a sine C. And now I'm going to use the other side of the triangle, so the one on the right here. And this distance right here, because the entire length was b, and we already used x, what remains is b minus x. So focusing on the triangle on the right now, there's a Pythagorean relationship between the sides. C squared, the hypotenuse squared, equals y squared, one leg squared, plus b minus x squared, the other leg squared. Now what I'm going to do is work on that equation and make some changes to it. So first of all, we could replace the y with a sine of c from above. And we could replace the x with a cosine of c from above. And then we can get rid of the parentheses because a times sine of c quantity squared is the same as a squared times sine squared c. And then we're going to need to multiply this whole thing by itself, so we're going to need to FOIL. And when we FOIL b minus a cosine c times b minus a cosine c, we end up with b squared minus 2ab cosine c plus a squared cosine squared c. Okay. Now, if I rearrange terms a little bit, we have c squared equals a squared sine squared c plus a squared cosine squared c plus b squared minus 2ab cosine c. And notice that the first two terms both contain a squared, so if we factor a squared out of those, we have c squared equals a squared times sine squared c plus cosine squared c plus b squared minus 2ab cosine c. And remember from the background information that sine squared theta plus cosine squared theta equals 1, no matter what the angle is. So that's true here as well. Sine squared c plus cosine squared c equals 1. So I have a times 1. So that gives me just c squared equals a squared plus b squared minus 2ab cosine c. So this is the relationship between all three sides of a triangle, an acute triangle, and one of the angles, angle C. So what we're hoping is that that will hold for the right triangle as well as the obtuse triangle so that we could use it for any triangle at all. So let's take a look at the right triangle case. And it's much simpler. So based on the Pythagorean theorem, we know that c squared equals a squared plus b squared. Well, hopefully you would agree that a squared plus b squared is equivalent to a squared plus b squared plus 0, or even minus 0. Doesn't feel like I've done very much, but remember that there are special forms of 0, and an example of that would be, you know angle C down here? For this special right triangle case, angle C measures 90 degrees. And what's the cosine of 90? It's actually 0. So I could replace my 0 with cosine 90 for this case. And you know, if you multiply 0 by something else, it's still 0. So I could replace it with, here's my 0, cosine 90. I could call it minus 2 times a times b times cosine 90. It's still 0. And 90 was angle C. So if I put a c in there where the 90 is, we have c squared equals a squared plus b squared minus 2ab cosine c. Same formula. That takes care of the right triangle case. And now we need to look at the obtuse triangle case. So we have an obtuse triangle, ABC, and this time I've put it on a coordinate system because I'm going to take advantage of the distance formula to help me with this part of the proof. And I've dropped a perpendicular from angle B across to the opposite side. So to find the cosine of angle C, I'm going to use the right triangle that's out here. And you know, to get the cosine, even though angle C is this angle here, the right triangle is the reference triangle. So using the reference triangle, we have adjacent over hypotenuse. That would be x over a. So if we solve for x, we have x equals a cosine C That should look familiar because we did that in part 1 with the acute triangle. And then same idea for the sine of C. Here's angle C, but this is its reference triangle. So for sine, we're going to do y over a. And we could isolate y. Y is a sine of C. And then to make a relationship between all three of these things, I'm going to use the distance formula. And I'm going to talk about the distance c, which goes from this point over here to this point over here. So what are the coordinates of point A? Well, it looks like the x-coordinate is b. And since point A is lying on the x-axis, its y-coordinate is 0. And what are the coordinates of point B? Well, we went x units left, and then we went y units up. So we'll just say it has coordinates x, y. And the distance formula, in case you don't remember, it's probably been a while since you've thought about it. The distance between 2 points is the square root of the difference in the x's, x sub 2 minus x sub 1 squared, plus the difference in the y's, y sub 2 minus y sub 1 squared. Now that distance formula is just based on the Pythagorean theorem. Okay, so using our points, the distance from point A to point B, which is little c, is the square root of, okay, the difference in the x-coordinates would be x minus b, and that gets squared. And the difference between the y-coordinates would be y minus 0, and that gets squared. And now we simplify this. So I'm going to square both sides of the equation, and that gives me c squared equals x minus b quantity squared plus, and then y minus 0 can be written as y, so just y squared. Now if you look at this equation, it's very much like an equation that we had back in part 1 when we were doing the acute triangle, except I had an b minus x instead of an x minus b. But if you're going to square it, it's the same thing. So c squared equals b minus x squared is the same thing as x minus b squared. And then for the rest of it, we would do exactly like what was done in the acute triangle case. Where we replaced x with a cosine c, and we replaced y with a sine c, and you're going to end up with the exact same result. So that takes us through all the cases and proves the law of cosine for every triangle.